Hello everyone. The central limit theorem is the most important theorem in probability and statistics. And basically it says if you have any population, it doesn't matter what is the probability distribution. It could be exponential, gamma, Poisson, binomial, and you take a large sample of size n, usually rule of thumb n larger than 30. Then the sample mean x, which is x1 plus x2 plus xn. So these are the data in this sample divided by n. Now the sample mean will have a normal distribution no matter what distribution is this, with mean mu of x bar and the variance of x bar. And we already found the average of a sample mean. It is just the mean of x1 plus the mean of x2 plus the mean of xn, and if these came from this population, so this would be mu plus mu plus mu, so you have n of them divided by n, you get mu. And the variance of x bar will be the variance of this one, which is sigma square, plus the variance of this sigma square, plus the variance of this sigma square, so you have n of them. So you have n sigma square divided by 1 over n, you square it because it's a constant, so that is sigma square over n. And we already showed that in previous slide and section. So that will be sigma square over n. So to summarize, any population data collected, measured, you don't know what kind of population they follow, or you take a sample of size 30, then the sample mean or the average of the data in the sample will have a normal distribution with a mean equal the mean of the population, and the variance will be the variance of the population divided by n, and that's this here. Now if I am interested in the sum of the data in the sample, so I am interested in S equal x1 plus x2 plus xn, then the mean of the sum will be the mean of x1 plus the mean of x2 plus the mean of xn. So I have n of them, so that is n mu. So then the sum will also have a normal distribution with mean n mu, and the variance of the sum will be the variance of x1, which is the variance of the population, the variance of x2, variance of the population, all the way plus the variance of x of n. So I have n of them here, so that is n the variance, and that's what this. So if I take a sample and I sum the data in the sample, then the sum will have a normal distribution with a mean n mu and a variance n sigma squared, and that will be the distribution of the mean. That means if another person take another sample here, then the difference between these and these will follow a normal distribution. Rule of thumb, the size of the sample must be larger than 30. And here is an example. This is a population with this probability distribution or density function. Now this is a sample mean of size 5. The solid line is the distribution of the sample mean x bar. The dot is a normal distribution, so it becomes closer when you compare them. Now if I increase the size to 30, they almost match. So the solid line, which is the probability distribution of the sample mean, almost like the dotted one, which is a normal distribution. Here is another distribution that is discrete. If I take a sample size of 5, again, now these boxes almost look like a normal distribution. Size of 30, perfect, a normal distribution. This is exponential distribution, which is way off from the normal distribution. If I take 5 sample, it starts becoming like a normal distribution, not perfectly, because we started with a total different distribution shape. You take a 30, almost the same. Let's take this example just to see the power of the central limit theorem. Let x denote the number of flaws in 1 inch length of copper wire. The probability mass function of x is this one. So of this population or manufacturing in this factory, we took a sample of size n 100. So 100 wire are sampled from this population. What is the probability that the average number of flaws in this sample is less than 50, the average number of flaws. So I have here a wire x1, another wire x2, another wire x3, another wire x100. And I am interested in what is the probability, the average, that means x bar less than 0.5. And we need to solve it. If we don't use the central limit theorem, it will be long. Just to give you an example. This sample here, I may have 50 wire with 0 flaws and another 50 wire with 1 flaw. That's a possibility. And the average flaws will be 0 times 50 plus 1 times 50 divided by the 100 wire. And that's half. So that's a combination. Now I need to find the probability that I will pull 50 with 0 flaws out of the 100 and 50 with 1 flaws out of the 100. And this is just one possibility, 50, 0, 50. I may get x bar less than half if I have 75 wire with 0 flaws and 25 wires with 1. Or 75, another possibility with 0 and 25 with 2. This is still going to give us the average of less. There are infinite possibility, and then for each possibility you have to calculate these. This is endless, but now the central limit theorem can solve it very easily. Because I am interested in the average and n is way more than 30, now I can approximate this average x bar as a normal distribution. Okay, so according to the central limit theorem, x bar will have a normal distribution with mu and a variance. First step, we have to find the mean and the variance of the population. And this is a discrete distribution, and we know the mean will be the first possible value of x is 0 times the probability x equals 0 is 0.48 plus second possibility for x is 1 times the probability 0.39 plus 2 times 0.12 plus the final possibility 3 times probability 0.01. So the mean here, if you do that, you should get 0.66. Now let's calculate the variance of the population. The variance of the population is the difference between the first value and the mean squared times the probability, which is 0.48, plus the difference between the second value from the mean squared times the probability, 0.39. Plus you do the same thing for the third possible value and the fourth possible value. And if you calculate these, you will get 0.5244. So now the mean of the sample is just the same as the mean of the population, which is 0.66. And the variance of the sample mean is just the variance of the population divided by n. So this is 0.5244 divided by 100. So this is 0.005244. So the sample mean x bar has a normal distribution with mean 0.66 and the variance 0.005244. And we want to find what is the probability x bar less than half meter, 0.5. So the probability that x bar less than 0.5 is the same as the probability the z-score less z naught. So we need to find the z naught that correspond to x equal half. So z naught will be, we use this, x naught minus mu over sigma. So z naught will be 0.5 minus mu, which is 0.66, divided by sigma, that is the square root of 0.005244. And if you calculate these, you will get minus 2.21. And if we use the table to look for minus 2.21, that's minus 2.2, and 1 is here, so that will be 0.0136. So probability x bar less than 0.5 same as probability z less than minus 2.21, and from the table we found it to be 0.0136. So there is a chance 1.36% that if you draw 100 wire from this population, the average flaws will be less than ½ inch. Let's take another example. The manufacturer of a certain part require two different machine operations. The time on machine 1, so let's draw machine 1 here, machine 2. The time on machine 1 has mean 0.4 hour and standard deviation 0.1. So that is 0.4 plus minus 0.1. The time on machine 2 has a mean 0.45 and the standard deviation 0.15. The time needed on the machine are independent. Good, so they are independent from each other. Suppose that 65 parts are manufactured. So this machine produce parts, so we took a sample of n equal 65. What is the distribution of the total time on machine 1? So we want to know what is the distribution on machine 1. Let's call that S1, system 1, and the total time on machine 2, and we need S2. So if I represent, this is the time for part 1, this is the time for part 2, part 3, all the way to part 65. So S1 is the total time, so that will be T1 plus T2 plus T65. And the same thing, same sample, this is the same sample, 65 part, but here let's call it tau. That's the time for machine 2. So that's tau 1. That's the time it takes for the second part, third part, tau 65. The time for the 65th part. Now, we use the central limit theorem. Then we know that S1 will have a normal distribution with mu S1 and a variance S1, which is the sum. So if I want to find mu S1, that will be mu T1 plus mu T2 plus all the way mu T65. And they told us the average time for this machine is 0.4. And they have 65 parts. So that would be the average time would be 65 times 0.4. And this should come 26 hours. And if I want to find the variance for S1, that will be the variance for T1 plus the variance for the time to do the second part all the way to the variance of the last part. And for the first machine, the standard deviation is 0.1. So that will be the variance 0.1 squared. And I have here 65 parts, so times 65. And if I calculate this, I should get 0.65. So the time it takes for machine 1 to make 65 parts follow a normal distribution with mean 26 hours and a variance 0.65 hours. And I can do the same thing for machine 2. S2 is the sum of all time to produce 65. So S2, the total time, will follow a normal distribution with mean N65 time 0.45 and a variance equals 65 times the square of the standard deviation, 0.15 squared. And this S2 will be a normal distribution of 29 hours, 0.25 with a variance 1.4625. And this is the distribution. For machine 1, it is this one. For machine 2, it's this one. Now they are asking, what is the probability that the total time used by both machines together is between 50 and 55 hours? First, we have to find the total time. The total time, let's call it ST, will be S1 plus S2. That's the time for machine 1, that's the time for machine 2. And they want to know what's the probability that total time ST between 50 hours and 55 hours. That's what they want. Well, S1 is a normal distribution. We just find out using the central limit theorem. S2 is a normal distribution. 2. So ST will be a normal distribution. And the mean of ST will be the mean of S1 plus the mean of S2. And that will be 26 plus 29.25. And that should give you 55.25. And the variance of ST will be the variance of S1 plus the variance of S2. And the variance of S1 is just 0.65 plus 1.4625. And if you add these, you should get 2.1125. So the random variable ST, which is the total time for system 1 and system 2 to produce 65 parts, will be a normal distribution with a mean 55.25 and a variance 2.1125. And to find this probability, it's the same as the probability of using the standard normal distribution. So I need to find the z-score for the 50 and the z-score for the 55. For the 50 will be this one, and for the 55 will be this one. So let's find the z-score for the 50. 50 minus the mean, which is 55.25 divided by the standard deviation, which is the square root of 2.1125. And this will be z1. And this should give us minus 3.62. And to find z2, this one, that corresponds to 55. That would be 55 minus the mean, 55.25, divided by the standard deviation, which is 2.1125. And this should give us minus 0.1726. And if we use the standard normal distribution table, probability of z larger than minus 3.62 and less than minus 0.1726 is the same as the probability z less than minus 0.1726 minus probability z less than minus 3.62. And if you use the table, you will find this probability 0.4325 minus 0.0001, and this is 0.4323. So that is 43.23%, and that's this one. So what's the probability that the total time used by both machines together is between 50 and 55 hours? It's 43% chance. Now, if you try to solve this problem without the central limit theorem, it will take forever. The central limit theorem can be used to approximate known distribution. It will make the solution much easier. And in this part, we will take two examples: how to approximate a binomial distribution and a Poisson distribution. So let's start with the binomial. So we have here a population. We are picking or conducting a Bernoulli trial n time, and our variable is x number of success. So now x is a random variable that has a binomial distribution with parameter n, the number of trial, times the probability of success. If this condition is met, np larger than 10 and n1 minus p is larger than 10, then this random variable, the binomial, can be approximated as a normal distribution with mu of the binomial and the variance of the binomial distribution. Just a reminder, for this binomial distribution, mu x is np, and the variance of x in previous sections we showed it's np1 minus p. So then x here will be a normal distribution with mean mu np and the variance this one np1 minus p. Also earlier we showed that if I have a binomial distribution and I conduct the experiment or the trial n very large such that np is larger than 10, then also I can approximate this binomial distribution as a Poisson distribution. So this also I can approximate it as a Poisson distribution with the parameter lambda, where lambda we showed equal n, the number of trial, times the probability. And we call this the rate of occurrence per unit time or per distance. So since this x is a Poisson distribution approximating the binomial and it met these two conditions, then also x, the Poisson distribution, can be approximated as a normal distribution with mean np, which is lambda, and the variance, we found the variance earlier of a Poisson distribution to be lambda. So then the variance of the normal distribution would be lambda. So you have a Poisson distribution like this one can be approximated as a normal distribution. You have a binomial distribution like this one also can be approximated as a normal distribution like this one. And this will help us to solve problem much easier and much faster with this approximation. The only thing you have to watch for is some adjustment you have to do, because normal distribution is a continuous density function, while Poisson distribution and the binomial distribution is a discrete distribution. Because of that, you have to be very careful in the continuity correction is an adjustment made when approximating a discrete distribution with a continuous one. Let me show you an example. If in the discrete binomial distribution I said what is the probability x equal or larger than 45 and equal or less than 55. So the end point here are included because of the equal. This is included in the probability because of the equal. So now when I approximate this discrete probability, which will be the area under this rectangular, when I approximate it by this continuous, that means I have to include this half for the continuous. So that means if I want to make this binomial distribution to a normal distribution, then the probability should be the following: x larger than, include this half. So that will be, if this is 45, then this will be 44.5, which is 45 minus half. So then I have to write here 44.5. And less than 55, that means I have to include this half area. So if this point is 55, then this will be 55 plus half. So that will be 55.5. Now, if I change the question and they said I need the probability x larger than 45 and less than 55. So now the endpoint are not included, they're exclusive. So when you look at this approximation here, larger than 45, that means that half should not be included because that's part of the 40 equal 45. So this half should not be included. And the same thing here, this half should not be included. So if I approximate this as a normal distribution, continuous, which is the solid curve, then it should be the area from here and the area under the solid curve to here. So that point here will be 45.5 half plus 45, and this point here will be 55 minus half. So then this should be probability x larger than 45.5 and less than 55 minus half is 54.5. And you have to take care of this correction. Now, if n is very large, then you probably don't need that correction, but it's good to always put that in your mind when you approximate a discrete distribution with a continuous distribution to include the endpoints. And that's what we have been saying here. So let's look at this example. If a fair coin is tossed 100 times, so I am conducting an experiment, n equal 100 times, use the normal curve to approximate the probability that the number of heads is between 45 and 55. So my x here is the numbers of heads, and they need the probability x inclusive equal or larger than 45 and less or equal 55. Now, if you try to solve this problem using the binomial distribution, then it will be very long. And if this problem came in the test, the 1 hour you have will not be enough. Because if you try to use a binomial distribution, that means you have to find the probability x equal 45 plus the probability x equal 46 all the way to the probability x equal 55. You have 11 probabilities you have to calculate. This one by itself, if you calculate it, probability x equal 45, it's n factorial, which is 100 factorial, divided by 45 factorial of heads and 55 factorials of tail, times the probability of head is 0.5, and there are 45 of them, times the probability of tail, 1 minus half is 0.5, and you have 55 of them. Just calculating 100 factorial, that takes a lot of time. Raising 0.5 to the power of 45, you better have a very accurate computer to calculate that. This will almost go to 0. And that's only the probability of 1 here. Then you have to do it 11 times, all the way to 11. But let's see now if we use the central limit theorem, how easy the problem will be. So if I approximate this as a normal distribution, so then x will have a normal distribution with mean NP. N is 100, probability of head is half, so that will be 50. So then x is a normal distribution with mean 50 and the variance NP times 1 minus p, so that is 50 times half times half. So that will be 25. So then the variance of n will be 25. Now I can solve the problem. Probability x, since 45 is included, I have to subtract a half from here and add half here. So that will be 44.5 and less than 55.5. And now I will use the z-score. I have to find z1 for this point here. So that will be 44.5 minus the mean divided by the standard deviation. And this will come minus 1.1. Now I need to find the z-score for this one. And this will be z of 2, 55.5 minus the mean 50 divided by the standard deviation. And this should come 1.1. So now I find the probability x larger than 44.5 and less than 55.5 is the same as the probability z larger than minus 1.1 and less than 1.1. And we use the table. This is the same as probability z less than 1.1 minus the probability z less than minus 1.1. And if you use the table, you should get 0.8643 minus 0.1357. And this is 0.7286. So there is a 72.86% chance that if you throw the coin 100 times, you will get heads between 45 and 55, 72.86% chance. See how easy it is to solve it using the central limit theorem in comparison to using the binomial distribution, which means I have to find 11 probabilities to come to this answer. Okay, let's take the second example here. The number of hits on a website follow a Poisson distribution with a mean 27 hits per hour. Find the probability that there will be 90 or more hits. So initially we have x is a Poisson distribution with a parameter lambda that is equal 27 hits per hour. And we need to find what's the probability x 90 or more hits per 3 hours. So the first task is convert this lambda instead of per hour to 3 hours. So then let's call this is the old lambda. So the new lambda now will be 27 times 3 hours. So that is 81 hits per 3 hours. So that's lambda. Just so we can find what's the probability or the number of hits is 90 or more in 3 hours. So now the new random variable x is a Poisson with lambda equal 81. We can solve this probability using Poisson, which is going to be really ridiculous. That means you're going to have to do 1 minus the probability x equal 1 plus the probability x equal 2 plus probability x equal 3 all the way to the probability x equal 90. Or use the central limit theorem and approximate these x as a normal distribution, since lambda is large 81, so NP is more than 10 and lambda is NP, so I can approximate it with big accuracy as a normal distribution. And as we showed before, the mean of this normal distribution will be lambda and the variance lambda. So x is a normal distribution with 81 and 81. Now I need the probability x equal or larger than 90. Now I have to convert these to a z, finding the z-score for x. So the z-score for x will be x, which is 90, minus the mean, which is 81, divided by the standard deviation, which is the square root of the variance, 81. And this will be 9 divided by 9, that's 1. So probability x larger than 90 is the same as the probability z equal or larger than 1 equal 1 minus the probability z less than 1, because the table only gives us the area to the left of z. And if I use the table, this will be 1 minus, and probability z less than 1 is 0.8413, and this should come 0.1587. That's 15% chance. So if the rate of hitting a website is 81 hit per 3 hours, then the probability you may get 90 hit per 3 hours will be 15% chance, 0.87. The last section in this chapter is simulation. And in simulation, sometimes we come up with an algorithm and we want to test the algorithm or a system and we want to test it. So we have to do a simulation, create data that may exist in real life as input to the system we are building. We use simulation to synthesize this data. So we can use this data to test our algorithm, to test our system, to see how good is it before we build it and test it on real life data or real life input. So let's just look at this simple example. An electrical engineer will connect two resistors labeled 125 in parallel. The actual resistance may differ from the labeled value. Denote the actual resistance of the resistors that are chosen by X and Y. So let's call this is X, let's call this is Y. The total resistance, since they are in parallel, R will be X times Y divided by X plus Y. Now assume that X here is a normal distribution with mean 100, a variance 100. And Y is a normal distribution with mean 25 and a variance 2.5 square. Let's make these 10 square. And the resistors are chosen independently. Assume that the specification for the resistance of the assembly is R should be between 19 and 21. They cannot be outside this range, otherwise our design will collapse. What is the probability that the assembly will meet the specification? In other words, what is the probability R will be between 19 and 21 for this system? So one way is to calculate what will be R and calculate also the uncertainty. And then we will come up with R equal plus minus certain value, uncertainty. And definitely if we calculate R here, it will be 100 times 25 divided by 100 plus 25. So these should come 20 ohm resistor. So we know for sure this R will be 20, but then the uncertainty here, that's the problem. Because R is not a linear combination of the two variables X and Y, so it will be difficult to find its standard deviation to calculate the probability R between 19 and 21. In this case, the best solution is to run a simulation. That means to generate possible values for x coming from these normal distribution and possible values for y coming from these normal distribution, and then calculate this value r and see what are the possible values for r and count. If we conduct the experiment 100 times or 1,000 times, then we count how many values of r fall in this range, and let's say 350 out of 1,000 simulation. Then the probability it will be in this range will be 350 divided by 1,000. And then it's up to engineer who's designing the system to accept these or go and buy a better resistors with a smaller variance. So how do you generate data for x from this population and y from this population? You can use a simple computer to generate all these values. Here is all possible value for x, here is all possible value for y, and they generated all the way to 100 value. And this is all the possibility for x, y. Then they calculate r equal x, y divided by x plus y. And they calculate for this value, they got r these. And they did for all of them. And these are the possible values for r. Now they can arrange these 100 possible value like this, from the smallest possible value for r to the largest value for r. And they count how many resistors here larger than 19 and less than 21, and they found 48 resistors fall in this range. So then the probability that r will be in this range will be 48 divided by total number of calculation 100. So that is 0.48. So there is only 48% chance that the two resistors connected in parallel will fall in this range. And here we showed how we generate data from a normal distribution. You can also generate data from other distribution, like this one, the lifetime in 1 month for a van. That will be exponential distribution. And I will leave this for you to read it in the textbook. All right, this ends chapter 4. Thank you.